So my name is Anurag Bambardekar, and today I will be presenting my research on SDR or software-defined radio-based emulation, machine learning-enabled spectrum sharing in 5G private networks. This work is the culmination of our efforts during the last 1 year as part of my master's degree in electrical and computer engineering. So in today's presentation, I would like to start off with an overview of the problem we addressed in this research, followed by the methods I used to tackle it. I will then present my key findings and conclude with a discussion on the implications of our work and potential future research directions. So, what are private 5G networks? So, as industries are growing more autonomous, the demand for higher bandwidth, low latency, and reliable communication is ever increasing. Private 5G networks, or they're also known as 5G non-public networks as per the 3GPP standard, they can meet these demands, which can potentially transform the industry landscapes by enabling more modern use cases and scalability. Um, Private 5G networks, they deliver the same benefits as public networks or public 5G networks, but they offer more control over policy, security, and data. They also offer better coverage for large spaces or even remote locations and access to shared spectrum while maintaining autonomy over the network. What are the key features? Low latency, high reliability, which supports real-time applications, dedicated spectrum and resources. So in some cases, private 5G networks have access to exclusive spectrum, or rather exclusive licensed spectrum. Enhanced security and control, which is again a critical feature of private networks. High bandwidth to support data intensive applications such as augmented reality and virtual reality. Scalability to easily expand the network capacity. And as per the recent 3GPP standards and upcoming 3GPP standards, it has been shown that it also has the potential to outperform Wi-Fi 6 and LTE. So Wi-Fi 6, although it offers fast, affordable deployments, but 5G private networks, they excel in security, control, and scalability, especially for industrial IoT and large-scale deployments. So in this diagram, you can see a simple comparison between or coexistence of 5G private networks. So in the blue bounded box, you have a private 5G network, and in the oval figure, you can see a public 5G network. And you have an optional connectivity if you want the private 5G network to fall back upon the public 5G network. Just would like to quickly go over the architecture and the various kinds of deployment of 5G non-private networks. 3GPP perspective says that there are only two deployment versions. There's the standalone non-private network, and then there's the public network integrated non-private network. So this graphic visually explains how different spectrum allocation methods such as licensed, unlicensed, and shared can be used to deploy private 5G networks. Um, so the yellow box is showing a virtualized private network that relies on a public licensed network, which is managed by a mobile network operator or a mobile or an MNO. So that involves technologies like network slicing, mobile edge computing, and so on and so forth. The blue box is depicting a completely private 5G network with its own dedicated license spectrum. The red box is showing a private 5G network which relies on dynamic sharing of the spectrum. So our research is focused in these sort of scenarios where we have to think about flexible and dynamic allocation of frequencies. And then the green box is showing another deployment scenario which is using unlicensed spectrum. Um, this would like to talk about the enablers or which is enabling or facilitating all of these deployment models. There's the network function virtualization, which really is about moving the network functions to software for flexibility. There's software-defined networking. There's network slicing and mobile edge computing. Another key fundamental technologies in 5G are millimeter wave, massive MIMO, beamforming, and so on and so forth. So, what are the industry trends? If if you look at the graph over here, it is depicting the projected growth of private networks across various industry verticals from 2019 to 2025. It's showing a 66% compound annual growth rate, and the vertical bars are representing the market size in billions of US dollars for different sectors. Um, Key points in this graph are that the utilities sector, the manufacturing sector, the utilities is shown by the green color, the manufacturing is shown by the orange, and the warehousing is shown by the yellow. So these are the three areas which is showing potential for significant expansion and increased adoption of private 5G networks. There are also other sectors like retail, wholesale, transportation, healthcare, and so on and so forth. Um, and I also I was working as a summer intern this past summer at this company called Molex, where I was working on smart building solutions. So I got an opportunity to interact with various companies like Cisco, Accenture, and Deloitte. And really, the key message that was communicated was, self-sustaining buildings. So they are more inclined to adopt private networks or 5G private networks in the future. Some of the recent applications would be, as recent as the Summer Olympics that just concluded in France. So the local telecom operator in Paris, Orange, is the name, I believe. They deployed private 5G networks for ultra low latency live broadcasting, especially for the water sports events where the cameras cannot go. So they use Samsung phones for it. In the US, Verizon has private 5G networks in the NFL stadiums for seamless communications. Um, and really, if you go back to the slide, FCC is leading efforts in the spectrum sharing for 5G networks with initiatives like CBRS or Citizens Broadband Radio Services and C-band auctions to optimize the spectrum use. And moreover, FCC innovation zones in the US promote wireless research and testing. And Cosmos testbed is also one of the first FCC innovation zones. Other than this, there is a huge push, as seen by the recent 3GPP releases, that AI/ML approaches are being embedded in the radio access network. ORAN is another movement, or Open Radio Access Network. It is promoting open and interoperable interfaces within the radio access network, which is really fostering a multi-vendor ecosystem. So it's supporting cloud native architectures, AI driven automation, and open interfaces. And finally, there's Open Test and Integration Centers, which is really focusing on validating 5G solutions from different vendors. Other than this, there are open source technologies available like Open RAN, SRS RAN, Open Air Interface, which is really facilitating research at the academia level. Now let's look at the spectrum. And really what we see on this slide is that we have nearly exhausted allocating the entire spectrum that is available. There is a lot of research going on in the millimeter wave, which is shown in this right end of this spectrum chart. So really in 5G spectrum, we are looking at FR1, which is also known as sub 6 gigahertz, and FR2, which is also known as millimeter wave. FR1 includes bands from 410 megahertz to about 7,000 megahertz, which is really ideal for broad coverage with moderate speed. FR2, it covers range from 24.25 gigahertz to 52.6 gigahertz. It provides ultra-fast speeds, but with limited range. And really, the focus of our research is in the FR1 band, more specifically the mid-band, or as 3GPP would like to call it, the N78 band, which ranges from 3.3 to 3.8 gigahertz. But in the US, the deployment is limited due to the existence of Department of Defense radars in this band. What we have is the CBRS band, or the Citizens Broadband Radio Services band, or the 3.5 gigahertz band, which is really designated as a sweet spot because it offers a good balance between range and speed. And it is enabling private 5G through dynamic spectrum sharing. FR3 is an emerging and intermediate band, but there's a lot of research going on in that area currently, and it is not really deployment ready at this moment. The key takeaway is that 5G spectrum sharing is a hot topic of research, and it aims to address the spectrum scarcity and maximize the utilization by enabling dynamic access for multiple users without interference. And this is really crucial for the growing demand driven by the increase in the mobile devices, IoT, and Industry 4.0. And there has also been this recent article by the NTIA, which is seeking funding to innovation in software-defined radio technology. And really, this spectrum sharing is what they are promoting. So, like I mentioned, mid-band frequencies is our area of interest for this research. So let's look at the existing uh, system that is in place in the CBRS band. So this system, or the engine is what FCC calls it, is the spectrum access system, which ensures the efficient spectrum sharing among the three tiers. So what are the three tiers in the CBRS band? So in this bottom left graphic, you can see you have tier one operators or the incumbents, which are the Department of Defense radars and military communications. Then there is the priority access license holders, and then there's the general authorized access. Um, so really what this spectrum access system is doing is it's coordinating the usage between the three tiers and managing real-time spectrum use. A key component, which is not mentioned on the slide, is the environmental sensing capability, or ESC, which is doing all of the spectrum sensing. And these are actually military or naval based sensors which are doing the spectrum sensing. Um, and other than this, we have the database, which is storing the spectrum availability and user data. We have the authorized center, which is protecting the incumbent users and detects spectrum opportunities for the tier two and tier three users. Um, and really, what I would like to focus on is the drawbacks of this current system. First drawback is the complexity of the spectrum access system. It has high operational costs, uh, and more importantly, it has a lot of service interruptions for the general authorized access users, which is the tier three users, which means that there is inconsistent availability, especially in congested areas. And also, who is making these systems? So the SAS providers include Google, Sony, Amdocs, and Federated Wireless. What are the possible potential improvements? As shown in the literature, people are really advocating for AI and ML techniques, which is really useful in high dimensional data scenarios, which really shows promise to improve the spectrum utilization and management. On this slide, we show some challenges that are documented in this private 5G networks area, especially we would be focusing on the first three, which is the mid-band frequencies area, spectrum sharing in co-located networks, and AI/ML integration for dynamic spectrum sharing. So, like previously mentioned, US is not only US, all over the world there is a spectrum shortage, and we need efficient spectrum sharing models, especially in mid-band ranges. Um, and we also need smart interference management, and we also need to think about coexisting with the existing networks in these bands. Um, Other than this, there are other challenges like security and privacy. It's a hot area of research in the context of private 5G networks. There are regulatory and compliance issues that certain research areas are tackling, and then there's scalability issues that some of the research is addressing. Some related work, just to put just contextualize the contributions of our work um, in the broader landscape of the research that is going on in this area. So we selected four papers to show on this slide. First is the coexistence of CBRS and naval radar systems. Um, and really the focus of this paper was mitigating the interference between naval radars and cellular systems using downlink power control. Um, while it relies on simulation without any real world experimentations, our work is really incorporating ML driven adaptive sharing. Uh, the other papers are talking about intelligent spectrum sharing, where it uses advanced models like neural networks. However, as you increase the complexity of models, interpreting the models or deploying these models in real time gets complicated and challenging. So we focus on simpler supervised and unsupervised models. Um, then the final paper that I would like to point out is the cognitive radio testbed. So as you can see from the previous slides, NTI is advocating for software-defined radios. So this paper, although it uses cognitive radio testbeds, however, it doesn't really use machine learning techniques, whereas our work focuses on ML enhanced spectrum reallocation and interference management, especially for private 5G networks. Okay, so let's talk about our work. This slide shows you the system model, and this proposed system model is really about optimizing the spectrum sharing between two co-located networks, um, or rather two co-located 5G private networks by utilizing a machine learning approach to predict the interference and dynamically adjust the frequency allocations. So, as illustrated in the figure, the model comprises two base stations, BS1 and BS2, and two user equipments, UE1 and UE2, that operate within separate but spatially co-located 5G networks. The communication between the base stations and the UEs in each network is facilitated by OFDM or orthogonal frequency division multiplexing, which is really a technology essential for high data rates and effective interference management. More importantly, we have the co-located sensors to the base station, which monitor the spectrum utilization and interference. And all of these nodes, they are providing crucial data to the spectrum manager. So the two networks that you see, which are being referred to as network one and network two. Network two is shown here as an interfering network to network one. And really, you can see that we are highlighting the degree of spectral overlap between the networks. So 100% means this network two is completely overlapping in frequency with network one. And we have shown all of the more granular overlaps in the system model as well. And really, the brain of this system model is the spectrum manager, which employs a machine learning model to predict interference levels and manage the frequency allocations dynamically. So it is collecting metrics like signal to interference noise ratio, packet error rate, power spectrum density. These are all being calculated and estimated. Um, and really, there's a machine learning model incorporated in this manager, which is doing the heavy lifting of predicting the overlap. So you can see there's a formula on the slide at the top, which is showing the predicted percentage of overlap, and it is given by this function of network one metrics and network two metrics that we are collecting. And really, the function is learned by the ML model, and the goal is to create generalized model so that when you give it an arbitrary overlap case, it can be identified by this model and the necessary frequency reallocations take place. This slide talks about the contributions that we have made in this as part of this research. So really, they are firstly, it is to develop a machine learning model which accurately predicts the interference levels. Um, the second some contribution is to create a dynamic spectrum manager, which minimizes the interference and optimizes the network performance. And finally, or more critically and importantly, it is the validation of the machine learning model that we trained through real world testing on the Cosmos testbed using software defined radios. So let's look at the experimental setup. Firstly, I would like to talk about the Cosmos testbed. So we conducted all of our experiments on the Cosmos sandbox, or more specifically, the Orbit grid. The Orbit grid is a 400 node 20 by 20 configuration. Uh, it involves USRPs, or Universal Software Radio Peripherals. Um, and these were used for emulating the co-located private 5G networks. The software-defined radios that we specifically used were the B210s, N210s, and the X310s. The B210s were used for the OFDM transmission and reception, which uh, happened between the base station and the user equipment. And the N210s were used as the co-located sensors to the base station. Um, Coming to the software part, we use GNU Radio, or GNU Radio, which is really an open source toolkit for developing SDR, or software defined radio applications. Other than this, for the post processing, for the exploratory data analysis, for the machine learning, we utilize Python programming language. More specifically, we use frameworks like scikit-learn and PyCaret. So scikit-learn is a widely used library. It has all of the classification and regression clustering algorithms. And PyCaret is also like a low-code machine learning library, which is really used to speed up the experiment cycles and simplify the process of training and validating multiple ML models in one shot. In this image, you can see the USRT E210s, which is hanging from the ceiling at the Orbit lab. Okay, so the first experimentation that we did was really to do some sanity checks, and this was done in a sandbox environment. So more specifically, we used Sandbox 4, or SB4, at the Orbit lab. So what it really consists of is that it consists of 10 nodes, each housed in RF enclosures, providing 80 decibels of isolation. This was really a non-over-the-air experiment, as it was a controlled test environment, and you can configure the USRTs to work this way. And really, the focus was on spatial variation, interference, and network performance analysis using these SDR nodes. In the left image, you can see that the nodes were arranged in a two-network configuration. The blue circles, they represent active SDR nodes functioning as transmitters and receivers for the two networks. The lines connecting the nodes, they indicate the network membership. So this can be considered as network 1, this can be considered as network 2. While the spatial distance between the two networks simulates the impact of spatial separation on signal transmission. So what we can do in Sandbox 4 is that we can increase or decrease the attenuation between any two nodes, or rather in this case, any two networks, and see the impact of spatial variation on signal transmission. The red circles here just represent inactive USRP nodes, and they have no effect on the operation of the two networks under study. And the gray nodes are again inactive or turned off USRP nodes. So what we do in this experiment is that we vary the attenuation between the networks and then record the observations. And specifically in this graph, you can see the effect of attenuation on the packet error rate in the networks, right? So you can see there's this blue curve, which is a 100% overlap case. 100% overlap meaning the both of the networks, they are having the same frequency. So let's say both are sharing the same center frequency of 3.5 gigahertz. So at even at a higher attenuation value, we are getting 100% overlap. So on the y-axis, you have packet error rate. On the x-axis, you have the attenuation. So the key takeaway is that as the attenuation decreases or as the networks move closer in spatial distance, the packet error rate increases, especially for networks with higher spectral overlap. And these results were really important in terms of providing insights and a simple sanity check of our OFDM transceivers and the collected data. And really, the results demonstrated that spatial variation and interference significantly affect the OFDM signal, especially as the networks move closer and interference increases. The next experiment that we moved on was actual over-the-air experiments. So here we have the two networks as previously seen in the system model. We have OFDM transmitters and receivers in each of the networks and a co-located sensor to the OFDM receiver. And the goal was to assess the real-world applicability of 5G spectrum sharing strategies by doing some over-the-air experiments on the grid testbed. What we are doing in this experiments is that we are running the OFDM receivers and transmitters and sensors on both the networks. We are varying the network two's operating frequency, or rather center frequency, to emulate a spectral overlap condition. So you can see we collected some metrics for a 0% overlap when they are completely separated in frequency. Then there's 25%, 50%, and even more granular overlaps. To incorporate spatial variations, since we have 400 nodes for our use, we can pretty much use any of the nodes to create spatial variations in reality. So the metrics that we collected were packet error rate, received signal power, SINR, channel occupancy, and also some FFT bins. The fixed variables for this experiment that we kept consistent throughout all of the experimentation and testing was the sample rate was 1 megahertz, packet length was 96 bytes, the header and payload modulation was binary phase shifting. Like I said, we fixed the network 1 center frequency and only varied the network 2 center frequency. And also the gain of the transmitter and the receiver were kept constant. So these were the topological. So this is actually a representation of the 400 nodes. You can see by the yellow and the orange boxes. So this can be thought of as one network, and this can be thought of as another network. So this is one topological variation that we use to collect the data. Similarly, this is another topological variation where this is now network. This is one network, and this is the second network. And we did see some obvious changes in packet error rate and other metrics. So similarly, we added like 8 more different variations of topologies just to emulate that spatial variation or incorporate that spatial variation into our final data set for machine learning training. Okay. So the system design, really there are 3 key components that I would like to talk about. The first one is the OFDM transceiver, which we implemented in no radio. And really what we are doing is, there's a frequency domain BPSK signal. We are using IFFT or inverse Fourier transform to convert it to a time domain signal. And then at the receiver, we are again doing FFT to convert it back to a frequency domain BPSK signal. The transmitter, what I would like to point out is that in Grow Radio, you can add some CRC32 bits to the data stream. Like I previously mentioned, we are using BPSK to modulate the header and the payload streams. And then we are adding the cyclic prefix, which is being only the key ingredient for OFDM transmissions. And one thing to note is that we are using different sync words for network isolation. So what are sync words? Sync words are they are crucial for synchronizing the transmitter and receiver in OFDM systems. They enable the receiver to detect the beginning of the transmission, correct the frequency offsets, and estimate the channel conditions, which are really essential for correctly decoding the transmitted data. And in GNU radio, sync words are implemented as part of the OFDM frame structure, and then they are processed by the receiver to ensure proper timing and frequency alignment. Um, so yeah, this meant that transmitter one and receiver one of network one can only hear and decode transmissions from its intended transmitter one, and similarly for the network two, right? Oh yeah, so here's the actual transmitted OFDM and the received OFDM. And this was, I believe, a scenario where there was no interference. So it's showing a good received signal. The next key component is the spectrum sensor. It really is doing two things primarily. We are doing the channel monitoring, and then we are doing the estimation of the SINR. So we used an out of tree module, or rather, in simpler terms, we had to install a separate module in the vanilla version of GNU Radio. And this module is called as GR Inspector, which is really to do some signal analysis. So primarily, we used two blocks that were of interest to us: signal detector block and the inspector GUI sync block. Signal detector block, what it is doing, it is performing a simple energy detection algorithm to detect the signals. So what we can possibly do is that we can either set a manual threshold, or we can also set some sensitivity parameters to do adaptive thresholding. Adaptive thresholding proved to be a difficult task to achieve. So we settled for a manual threshold. So we set it at minus 70 dB for detecting the presence of signals across specific channels. So you can see we decided to fix the number of channels to 10. And really what we're doing is that channel one is, let's say, monitoring 1 megahertz around 3.495 gigahertz, and so on and so forth. And on the right, you can see this illustration where it's detecting the signals. And across time, it is counting how many signals it's observing within each channel. And at the end of the day, we are just aggregating the number of observations in each channel. The second part is the SINR estimation, which is another challenging task, especially with radio and software-defined radios. And really, what we had to do was we had to introduce an enhanced SINR formula to account for the interference, because we, especially in 100% overlap cases, uh, it was not really, the SINR metric was not really making any sense. Uh, and this is primarily because we had a very simple implementation of calculating the SINR, where we had designated a part of the spectrum. So here you can see this part was designated as a desired signal, whereas the rest of the spectrum, that was really the noise, and we were calculating it as such. However, we weren't doing any OFDM decoding. So, case of 100% overlap, where the frequencies like overlap completely, it was hard to tell. Like using the normal SINR formula, there was not really a way of discerning the desired signal from the interference.
Can I ask something? Is this simulated channels or it's real?
This is real channels. So we came up with like 10 different channels. So the first channel, like I mentioned, we were monitoring 1 megahertz around this 3.495 gigahertz center frequency. And really, you can see this vertical red lines. It is the detected signals, right? And we are counting how many of those signals it is finding in that 1 megahertz channel.
Yeah, thank you.
Third component that I would like to talk about is the spectrum manager framework, which is essentially all encapsulated in a simple bash script or a shell script. And what we are essentially doing is we are first initializing the network components using the predefined variables that we discussed about. We are collecting the network metrics, packet error rate, signal to interference noise ratio, and so on and so forth. Then we have a pre-trained XGBoost model, which is doing the interference detection. And then we have a simple frequency reassignment strategy, which is doing the frequency reallocation. And really, the goal was to not complicate this frequency reassignment strategy because network operators can come up with their own predefined quality of service metrics. And this whole process is an iterative process where the network conditions are reevaluated and frequency reassignment continues until the packet error rate drops down to, let's say, 0%. Why 125 kilohertz, you might ask, is because this 125 kilohertz shift, it aligns with the 9 classes, or rather 9 overlap scenarios that we have used for training the machine learning model, where each class corresponds to a specific frequency band. So what we are essentially doing is that if we increase the interfering frequency by 125 kilohertz, it effectively lands into the next channel, right? So we had 10 channels. So let's say if we see an interference happening in channel 5, we are basically telling it to go to the next channel. Right? If I would like to draw some comparisons to the existing CBRS spectrum access system, it both reallocates frequencies dynamically to mitigate the interference. In CBRS, however, there are much more lead times for frequency reallocation. I think it's around 300 seconds or something. But if more critically, if you are like a GAA or a general authorized access user, then you really have no choice other than to wait for the incumbent user to vacate the frequency. Okay, so let's move on to the exploratory data.
Hey, Anurag, I just wanted to alert you to time, okay? Just be aware.
Yes. So the exploratory data analysis, we collected over 15,000 data points. We had 16 overlap scenarios that we decided, which included granular overlaps as well for testing purposes. We handled, as goes with any machine learning data set, we had the usual issues of missing values and erroneous values. So we fixed the missing values using nearest neighbor imputation. Other imputation methods exist, like mean imputation, which is really calculating the mean and imputing the same value at the missing cells. That was really simplistic, so we settled for a k nearest neighbor imputation. We created 3 data sets, a 2-class data set, 4, and a 9-class data set, each with 1,000 data points. What it really means is that for the 2-class data set, we had a 0% overlap and a 100% overlap case, and so on and so forth for the 9-class and the 4-class data set. We collected around 160 features actually. So dimensionality reduction was needed. So we performed principal component analysis, which retained the components which explained over 95% of variance of the data set. So this meant that we reduced the number of features to around 30 or 35. In addition to this, we also engineered new features. I think we are engineered around 11 new features, which included power ratios and spectral entropy. And really, it served 2 purposes. One was to increase the model accuracy which it did. And the other was to actually learn what the data is really about, especially in cases where you have like 64 FFT bins, it's really hard to tell what's really happening in the data set. So we also plot some correlation heat maps, which reveal significant correlations between the FFT bins. And really, all of this process was really to reduce dimensionality of the data set. The next part of this exploratory data analysis is just to look at some critical parameters like packet error rate, received signal power, and FFT bins. Packet error rate, as is obvious, it increased with higher overlap and stabilizing around 80% or 100% overlap. So for analyzing all of these metrics, we used box plots and scatter plots, which were really helpful. Received signal power, it remained stable, but decreased slightly in higher overlap scenarios. There was also some variability in the signal power, which increased with overlap due to interference. Higher FFT bins showed increased power and variability in high overlap scenarios. But like I previously mentioned, the SINR estimates that we calculated, it showed inflated values under high overlap or especially in 100% overlap cases, which we fixed it with ESINR metrics. So this is just a simple graph which is showing the relation between the packet error rate on the y-axis and the overlap percentage on the x-axis. So you can see in 0% overlap, and this is, mind you, this is like a aggregated packet error rate. So you can see the interquartile range is also illustrated in this figure, which is showing that in 0% overlap case, the packet error rate was as low as 15%. Right? And even for the 100% overlap case, we saw some variability. And this is really attributing to the fact that we use like topological variations in our data set. Supervised learning, just would like to quickly go over this slide. The objective was to create a multi-class classification model which predicts the interference between collocated private 5G networks. In our data set, we had the feature vectors and the labels. The labels were really corresponding to the 9 overlap scenarios that we discussed, ranging from 0% overlap indicated by class 0 and the 100% overlap indicated by class A. The classification algorithms that we use were primarily logistic regression, k nearest neighbors, and random forest. And the evaluation metrics, as is associated with supervised learning, is accuracy, precision, recall, and F1 score. Similarly, for the unsupervised learning, the objective was to identify clusters in network performance data that we collected, which could reveal or potentially reveal interference pattern. And really, the expectation was to see if the clusters can detect the different interference levels. And the key thing to note over here is that as it's an unsupervised learning, there's no labels that are being fed into the machine learning model. The models that we use were k-means, hierarchical clustering, and density-based methods that were the focus of unsupervised learning. And silhouette scores and elbow methods were the metrics used to evaluate these models. So these are the performance insights of the supervised models. XGBoost model was found out to be the best performing model out of a whole other. So we actually use the PyCaret framework, which enables you to use multiple models and compare their performance. So XGBoost model, confusion matrix showed most accurate prediction for class 0 and class 8. So I'll show you the graphs for the confusion matrix and the ROCAUC curve. So some other models that we saw were performing as good as extreme gradient boosting model was the light gradient boosting model. Then there was also simpler random forest logistic regression models. And mind you, this table is showing the test accuracy scores for the 9+ dataset. So these are the graphs that I was talking about, the confusion matrix. Just to quickly go over the confusion matrix, the rows are showing the true class labels, while the columns are showing the predicted class labels. The diagonal cells, which are represented in green color, they're showing the number of correct predictions for each class where the true class and predicted class match. And the off diagonal cells are showing the misclassification. So you can see it is very good at predicting like a 0% overlap case and a 100% overlap case. But as it encounters more granular overlaps, there are some misclassifications also. Then the ROC, on the right, you can see the ROC curves, or the receiver operating characteristic curves, which really visualizes the classifier's performance across various threshold values. So it essentially plots the true positive rate against the false positive rate. And each line is representing the ROC curve for one of the classes. It shows how well the model distinguishes between the true class and the other classes. And this is what we ideally expect all of the curves to be as close to 1. What we don't want is the curves to be closer to the diagonal line. So most classes have an area of under the curve of 1, which is showing excellent classification performance. Other classes are also showing strong performance with values ranging from 0.97 to 0.99. So unsupervised models, the results are not as great as expected, and that also reflects the challenges of spectrum sharing using unsupervised model. And really, the drawback of the supervised model is that we needed labeling of the dataset, which is not really possible in real time. So unsupervised models is ideally what we want. So for the 9+ dataset, it showed a low silhouette score, and we want the score to be as close as 1. So that suggests a very moderately low degree of separation between the clusters. As you can see, this is the PCA plot for the 2+ dataset. So there is 100% overlap and 0% overlap dataset. And this was implemented, and this is the result of the k-means clustering algorithm. So you can see there is a decent amount of separation. However, the silhouette score was not really agreeing with the results that we saw. And also the confusion matrix revealed that the clusters that it was assigning, that was not really matching up to the actual ground truth of the observations. Hierarchical clustering was similar. The 9+ dataset, very poor clustering performance, substantial overlap between the observed clusters. It performed surprisingly well on the 2+ dataset, and also the confusion matrix agreed with the results. However, the trend was that as you increase the number of classes, or rather, if you increase the number of overlapping cases, there is you're increasing the complexity, and the clustering algorithms need some hyperparameter tuning or more optimization to perform well. So some other models that we tried were Gaussian mixture models and DB-scan algorithms, which also similarly struggled.
So may I ask, excuse me, Anurag, may I ask here a question? So why do you think the previous unsupervised algorithms, what is your thought, why did they not perform well?
So I think what it really requires is the good feature engineering. So one of the things that is critical for training unsupervised models is that it requires very good data, very clean data, and you need to engineer what is really essential and critical is selection of the features. So even though we we employed principal component analysis to reduce the dimensionality of the data, which captures about 95% of the variance in the data set. However, it is losing that 5% of variance, which might be critical for the unsupervised model to to form separate clusters. I think that might be a reason. Feature engineering could be better. Although we engineered about 11 in new features, they could be like simplistic engineered features. So maybe someone could look at like engineering actual critical features and go step by step and evaluate incorporating some of the features and evaluating the unsupervised models. So I think those are the reasons.
Did you use data from different topologies altogether, or
Yes. So I
did
think
you
that's
try
another.
from one topology only?
I don't think we tried that because really the expectation was to gather as much variation in the data set and create a very robust data set and then see if the unsupervised model can learn. But I do acknowledge that we should have tried like getting data from like a single topology and see the performance of like an unsupervised model. Okay, so as a compromise, there's another approach in machine learning, which is really semi-supervised models, which takes in labeled as well as unlabeled data sets. So really the two algorithms in focus for semi-supervised learning was label propagation and label spreading. What label propagation does is that it's actually creating a graph of connected data points, and it's propagating the labels across the graph. And in label spreading, label spreading is similar to label propagation, but there is an added regularization parameter that smooths the label distribution over the graph. Coming to the results, two-class data set, it was excellently performing, showed about 95% accuracy, high F1 scores, strong precision and recall. Four-class data set, like I previously mentioned, with clustering, as you increase the complexity, the accuracy is dropping down, which is reflecting the increased complexity. Although for the 9-class data set, it dropped down to about 84%, which is comparable to the XGBoost model, which is a supervised model, which is also a preferred model for this recent work. So I think if you do the necessary hyperparameter tuning properly for the semi-supervised learning algorithm, I think you can increase the accuracy with semi-supervised models. And this is a good approach because you can afford to have a limited number of labels in your data set, and then it can work off the unlabeled data set. So you can, let's say, have a 20% labeled data set and 80% of the data set would be unlabeled. Another critical thing was real-time performance on the Cosmos testbed. For this, what we did was we had network 1 set at 3.5 gigahertz, and we set the network to also on the same center frequency to create a worst case overlap. The testing happened in two phases. The first one was we collected the data and we did some offline testing, but this time we incorporated unseen granular overlaps which were not used in training. So overlaps like 30%, 32%, 40%, and so on and so forth. So we achieved a pseudo accuracy of about 71%, which actually is a good result. It demonstrates the model's generalization to varying overlaps. What is pseudo accuracy? I mean, since it was a supervised model, there was not really any ground truth or labels to verify the accuracy for the new granular overlaps. So what we settled for was that even if it was predicting 25% overlap or a 35% overlap, when in actual reality it was 30% overlap, we accounted that as a success. But if it was like more than that and completely misclassifying, then that was penalized. Then we also evaluated the frequency reassignment strategy, and this was actually in real time. And the quality of service metric that we chose was to reduce the spectral overlap to 0%. And this also showed about an 80% or 79% rather accuracy, which also highlights the model's adaptability in real-time interference management. And these are some graphs. So on the left, you can see the mean network 1 packet error rate. So like previously mentioned, network 2 was the interfering frequency. So we were interested in looking at the packet error rate of network 1. And really, it shows that the packet error rate decreases steadily as the interfering frequency moves away from the network 1's operating band. And on the right-hand side, you can see the mean SINR for network 1 and network 2. So I'm not sure if you can see it. But in the boxes, you can see the actual overlapping scenario and the predicted overlapping scenario. So it has some good predictions. So predicted accurately for the 100% overlap case, and so on and so forth, until we reach the so even though so just to recall, 3.5 gigahertz was the center frequency of network 1 with a 1 megahertz allocation. And as soon as theoretically possible, if network 2 is operating on 3.501 gigahertz with a 1 megahertz bandwidth, although theoretically we can see that it is separate in frequency, it is still predicting that it is 12.5% overlap. And it's only until when it reaches 3.50165, I believe, gigahertz center frequency, that it actually predicts that, it was 0%. So we suspect that this could be due to existing channel interference or intermodulation products that is really attributing to the collected metrics in this region beyond 3.501. And it's saying that, it is not, you will not get like a good packet error, like a packet success rate if you operate in this region. So let's see. All right. So the conclusion was that XGBoost was the most preferred model for our use case. Performed well on real-time data. We also validated it on the Cosmos testbed. Clustering, as we know, it struggled with high-dimensional data. Semi-supervised models was selected as a good alternative which achieved comparable accuracy, the XGBoost model. And most importantly, and this is also something that I observed in the literature, was that real-world testing is quite minimal. A lot of simulations using tools like LabVIEW and all of that stuff. Future work, there's a lot of research going on in this area, showing a lot of promise, and we are getting one step closer every day. Specifically to this area, maybe someone can look at advanced clustering techniques and even deep learning frameworks. Deep learning frameworks are known for better feature extraction and class separation. Reinforcement learning is the most popular choice in this area, as seen across the literature. And yes, it is actually more preferable for real-time adaptability in spectrum management. And also, there are some challenging and ambitious future work that someone can do in context of spectrum scheduling. And I think that's it. Before I take any questions, I would like to express my deepest gratitude to my advisors, Professor Mandeyam and Ivan Shishkar, for their encouragement and insightful guidance throughout my research journey at WinLab. Their expertise in this area and discussions and continuous support have been instrumental in bringing this research to its present form. Thank you to my committee members as well. I'd also like to thank my collaborators, Prashanti and Shira, whose expertise and contributions were crucial. And I think I can take some questions.
Okay, thanks, Anurag. Any questions? I know we had some, but
I can make a comment.
Yeah.
Good work, Anurag. I think you said it in your final slide that maybe reinforcement learning would be a good approach here. If you have a model about how the environment changes, in order to be able to predict, you need to have some knowledge about how the environment changes. And a reinforcement learning approach would be good for this.
Yes, yeah, for sure. I mean, even at WinLab, I remember reading this paper by the student, I think his name is Neil Krishnan. He did some research in distributed MIMO, and especially in Wi-Fi networks, and he used reinforcement learning for allocating resources to the multiple Wi-Fi networks in close proximity. And even other than this, there are, it's the most popular choice that I encountered across the whole literature.
Yeah, Neil did that as part of his thesis. Yeah, he worked with Ivan and me. Okay, any other questions? All right, I have a question. Yeah, go ahead. No, go ahead, Marie. No, you
also comment because Athena gave me this now this idea, because for future work, indeed, it would be very important to see what are the anticipated needs for services, for even for the spectrum analysis, for finding understanding better where there are coincides, where there are collocations, and for the topology, and so that then you can reapply the models. So that would be a nice conclusion for a nice research direction for the future. But the other comment I also have to make is that personally I enjoyed reading and today your presentation, because it had a very good flow, important information. So you gave all the pieces of the puzzle to the extent of the work that you did, and it was very interesting because I think this was really a full, very good work.
Thank you.
Congratulations.
Thanks.
Yeah, so I have a question, Anurag, related to the future work. So why aren't you staying back to do a PhD? It's my question to you.
So honestly, so when I came to the US, frankly speaking, research was not at the top of my list of things to do, and especially writing a thesis. But as things progress and as the courses that I took, it involved me reading a lot of research papers, and it inculcated that habit of digging deeper into certain areas and topics, and it especially the summer that I spent at WinLab. I think it was the last summer when I was working with the summer interns on different projects, and especially 5G and 6G, future G, as people are calling it. Those areas really interested me, primarily because I have an undergrad degree in electronics and telecom engineering. So I felt I was putting some of the skills I use also in this research. But yeah, I never really thought of doing a PhD. I really wanted to get some experience in the industry, work out there in the field, travel. Yeah, so those are some of the things that I want to tick off my bucket list. But yeah, PhD, I'm not entirely declining the opportunity to do a PhD someday in the future. I do think I would like to pick up things somewhere in the future, but
But to follow up on Narayan's question with a comment, industry wants PhDs and they pay them really well.
Yes, for sure. But yeah, I made some friends along the way who are current PhD students, and I realized that it requires a lot of dedication, and which I do think that I would be dedicated to the work and be committed, and it's a really interesting area of research. But I just think that at this stage of life, I'm just exploring things and still figuring out what is best for me. I think at the moment I feel industry experience would be more suitable. I feel, but yeah, who knows? I mean, in the next few years, I might come back.
Maybe coming back after this insight and experiences, you come back more focused. This usually happens, and you can complete your PhD faster and with more significance. Narag and I had the same question at first for Anurag, because I met Anurag through some courses I was teaching, and he was maybe he was the best student, if not one of the best, because of his maturity and of his ability to and the interest to dig deeper, not just to leave things where they are, but to understand and get insight in all the questions, all the problems. So I think he would be one of the ideal students to at some point come back for PhD.